Hello and welcome to Mike Academy. So in this video, we are going to be looking at the Newton-Raphson's method of numerical methods involving two variables. The Newton-Raphson's method involving two variables is simply a numerical technique which is used to approximate the root of a given nonlinear equation. The equation is usually of the form f of x, y equal to 0 and g of x, y equal to 0. So you can call the first equation 1, you can call the second equation 2. Now, to approximate such nonlinear equation, the Newton-Raphson's formula to use is given simply as you have xn plus 1, yn plus 1 to be equal to you have xn, yn minus the Jacobian inverse of the function xn yn multiplied by the function or the matrix of the function xn yn. Now, where f of xn yn simply means the matrix of the given function. Now, mathematically, f of xn yn is equal to the matrix of f of xn yn and g of xn yn. So this gives us the matrix of the function at an initial guess. So if you have up to 3 equations, it simply means the third equation will take the third row, just as the first equation takes the first row, the second equation takes the second row. Then again, the Jacobian inverse can be found firstly by obtaining the Jacobian of the function at a given point, right? So we need to first of all find the Jacobian of the function, Jacobian of xn yn, and that is simply given as a matrix of partial derivatives. So you have partial f all over partial x, again partial f all over partial y, then you have partial g over partial x, you have partial g over partial y. So you have this. So in a situation where you have up to 3 variables in that equation, that means you're going to be having like 3 equations. In that case, you have to remember the first equation will always take the first row. So you have partial f, which is the first equation, the all over partial x, then again partial f over partial y. If there's a third variable, it becomes partial f all over partial z. Okay, same thing goes for g, which is the second equation, and again the third equation. So the first equation takes the first row, second equation takes the second row, and the third equation takes the third row. Now this is actually the Jacobian of the given function. Now you have to evaluate these partial derivatives at a given point, xn and yn. Now xn and yn can be your initial guess. Then after obtaining your initial guess and getting the first iteration, then xn and yn cannot be resubstituted into the given equation again for the Jacobian and for the function matrix to obtain a new value of the function matrix and a new value of the Jacobian matrix, so you can be able to find your inverse Jacobian. Now, having gotten your Jacobian, the next thing to do is to find the determinant of the Jacobian. After obtaining the Jacobian of the matrix of the given equation, the next thing you do is to find the determinant of Jacobian. So you simply find delta j of xn yn. So simply obtain the determinant of the Jacobian. Now, after obtaining the determinant of the Jacobian, from the formula, we need to find the Jacobian inverse of the given function. So the Jacobian inverse is taken simply as Jacobian inverse of xn yn is simply taken as, first you take the inverse or the inverse of the determinant, so delta j of xn yn. You find the inverse of the Jacobian, then you multiply it by transposing the measure diagonal of the matrix. So partial f partial x takes over partial g partial y. Meanwhile, partial g partial y takes over partial f partial x. So this simply becomes now partial g over partial y. Then you have here partial f all over partial x. Then you negate the minor diagonals. You may negate the minor diagonals. So I'll simply have negative partial g over partial x. I'll have negative partial y, partial f all over partial y, and you have this. Now, these two products simply gives us Jacobian inverse of that given function. So whenever you're given a nonlinear equation, this is the formula you use to approximate using Newton-Raphson's method, right? Now, xn plus 1 simply means the next approximate value for x. That is after your first iteration or after your successive iterations, right? Then yn plus 1 also means the next approximate value for y after your successive iterations have been carried out. Meanwhile, xn and yn simply means the current value after your iteration. So let's say, for instance, you're given an equation and you take your initial guess starting from when n is equal to 0. So you can simply replace that. This becomes x naught and this becomes y naught. Okay, so once you obtain your Jacobian inverse, find your the matrix of the function, evaluate it at a given point, then you can simply plug into this formula and find your xn and find your x1 and y1. That's for the first iteration. You do that repeatedly until the values of s converge and the values of y converge. Now we're going to pick a simple example, to explain this everything we've learned here. Now it is also important for you to know that when carrying out Newton-Raphson's method involving nonlinear equations, you might in most cases not be given an initial guess. So if you're not given an initial guess, the way to find your initial guess is to assume two values, the same values for both x and the same values for both y, such that when you plug them into the given equation, it will turn the first equation into positive and turn the second equation into negative, or it will turn the first equation into negative and turn the second equation into positive. So what I'm simply saying is, if you're not given an initial guess, that means you're at liberty now to choose an initial guess. You start from the smallest value, let's say from 0. You make x to be 0, you make y to be 0. Then you substitute into the equation given to you. If it turns the function to be negative, the first equation to be negative, and turns the second equation to be positive, it means the root can lie there. But if it doesn't, then you cannot choose 1 and 1. Okay, then try it again. So that's how you choose your initial guess in this situation when you're not given an initial guess. But if you're given an initial guess, you can simply go ahead and use what is given to you and substitute into the equation and solve. Now let's take for an example. Let's say we are asked to find the root of the equation. Let's say we're asked to find the root of the equation x squared plus y squared minus 4 equal to 0. This is equation 1. And then you're asked to find exponential x plus y minus 1 is equal to 0. This is equation 2. Let's say we're asked to approximate the root of this equation using the Newton-Raphson's method. Okay, so like I said, the first thing to do now is to pick out your initial guess, because in this question we're not given an initial guess. So it is important for you to know that this equation is of the form f of xy and g of xy, because you have two different equations, non-linear. So you have to start by what? Picking up your initial guess. So let's try when x and y is 0. Since we are not given initial guess, we can simply say let x be equal to y, that's equal to 0. So if you put in these values of x and y at 0 into the equations, let's start with equation 1. Equation 1 will simply give us 0 squared plus 0 squared again minus 4 equal to 0. So this answer will simply give us negative 4, right? The result simply gives us negative 4. Now this is for f of x, y. So this simply means that my first function f of x, y is equal to minus 4, and this is what? Negative. Perfect. Now all we need now is for the second equation to turn into positive. Then it means the root of the equation will lie at 0 or lie between 0, right? Then we can simply start our iteration. But now let's plug into the second equation. Second equation stands for g of x, y. So this is going to be equal to, now I have exponential x, and x is 0. That becomes exponential 0 plus y is also 0 minus 1. Now this simply gives us exponential 0 is 1. Of course, 0 here is nothing, is off. Then you have 1 minus 1, which is actually what? 0. And this is not what we want. We want a situation where 1 is positive and 1 is negative, or 1 is negative and vice versa. So we're having 1 to be negative and the other to be 0. It means it doesn't work. We have to now try the next guess. So let's simply assume now that x is equal to 1, or x is equal to y and is equal to 1. Let all of them be 1. Let us now find f of x y, which is actually f of 1 1, right? So for the first equation, I have x squared plus y squared. That is 1 squared plus 1 squared minus 4. This is actually going to be 1 squared is 1 plus 1 squared. That's 1 plus 1 is 2 minus 4. That is negative 2. So once again, this is what? Negative. You try the second equation, g of x y, which is actually g of 1 1. You have exponential x there, which is exponential 1 because x is 1. Okay, plus 1, y is 1, minus 1. So minus 1. So 1 minus 1 is actually 0. You have exponential 1. Exponential 1 is approximately 2.718. And this value is what? Positive. So it simply means that the root of the equation lies between 1 and 1. So we can simply proceed with x as 1 and y as 1 for our initial guess. So this simply implies that when n is equal to 0, when n is equal to 0, we are simply saying x is equal to 1 and y is equal to 1. So we simply use this to start our iteration. Now we know the initial guesses. We can now start the first iteration. Okay. All right. So let's perform the first iteration. First iteration. That is when n is equal to 0. So remember, this is the formula we are obeying, right? So first of all, let us find the matrix of the function, and then we need to find the Jacobian as well. So let's start with the matrix of the function. We need to find f of xn, yn. In this case now, n is 0, so this becomes x naught, y naught. This is actually, remember the formula, it is simply a matrix of f of xn, or f of x naught, y naught in this case, then g of x naught, y naught. So you simply have this. Okay, so let us find this matrix. This simply means we should find the value of the function at x naught and y naught, and the values of the functions that for the first equation and second equation at x naught and y naught. So we can simply do that here. So remember, I said the first equation simply means f of x y, okay, equal to this, and the second equation is simply g of x y, which is equal to this. So let us find f of x naught, y naught. So f of x naught, y naught simply means plugging the value of initial guess into the function, and we took our initial guesses to be what? 1 and 1. So if you plug in into this equation, you're going to have, for the first equation there, 1 squared plus 1 squared minus 4. This simply gives us negative 2. 1 squared plus 1 squared is 2. 2 minus 2 is simply negative 2. Next, you find g of x naught, y naught. And this is going to be equal to exponential 1 plus 1 minus 1. And that's going to give us 1 minus 1 is 0. Exponential 1 itself is 2.718. So you have 2.718. So this simply means that we know the values of the function at that point. Therefore, the matrix of the function is going to be equal to, you simply have, for the first matrix, which is matrix of the first function, you have negative 2. And matrix of the second function, we have 2.718. So this becomes the matrix of the first, or the matrix of this function, f of x, y. It's as simple as that. The next thing to do is to what? Compute the Jacobian inverse. But to find the Jacobian inverse, we have to first of all find the Jacobian matrix of the given function, right? So remember, Jacobian of x naught, y naught is now going to be equal to, so the Jacobian matrix is simply partial of f over partial x, partial derivative of f over partial y, partial derivative of f all over partial, second equation now, partial derivative of g over partial x, partial g all over partial y, and you have this. So this is going to be equal to, so it means that we have to partially differentiate the first equation with respect to x and with respect to y. Now, this is our first equation. If I differentiate this function with respect to x, I will simply have 2x partially. I will have 2x. So we have here 2x. If I differentiate that same equation with respect to y, I will simply have 2y. this now becomes a constant, and this now becomes a constant that goes up. So I will simply have 2y. So we have 2y. So the first equation takes the first row, right? Now the second equation takes the second row. So we need to find partial g partial x, partial g partial y. So you move over here now. This is g now. If I differentiate g with respect to x alone, that means y and -1 becomes a constant. The derivative will give us 0. But if I differentiate exponential x, I will still have exponential x left. Okay. Next, you differentiate g with respect to y. If I differentiate g with respect to y, this is simply just y, and that will give me what? 1. So I have 1 here. So remember, you are to find this Jacobian at the initial guess, x0 and y0. And x0 and y0 is simply what? 1 and 1 when n is equal to 0. So you simply plug in their values into the matrix. X is 1, okay? So you have 2x, that is 2 times 1. That gives us 2. Y is also 1. 2 times 1 also gives us 2. I have exponential x. X is 1. Exponential 1 gives us 2.718. Then I have 1 here, simply 1. So this becomes the Jacobian of the given what? Equation, right? Now, after obtaining the Jacobian, the next thing to do is to find the determinant of the Jacobian. When you obtain the determinant of Jacobian, you use it to multiply by the transpose of the major diagonal of the Jacobian and then negating the minor diagonal. It's as simple as that. That gives you your what? Jacobian inverse. So let's do this and see. We now find determinant delta of Jacobian x0, y0. We find the determinant of that matrix. That simply gives us, remember, to find determinant, your first sign is positive, next sign is negative. So you pick the very first element there, plus 2. You have plus 2. So it becomes this element multiplied by since it's a 2 by 2 matrix, it becomes plus 2 times 1. So I have plus 2 multiplied by 1. Then minus the minor diagonal now, 2.718 multiplies by 2. So I have minus 2 times 2.718, whichever it is, minus 2 times 2.718, and you have this. So this gives us our determinants, right? So let's evaluate all of them together just to save time. So upon evaluation, we simply have negative 3.436 for the determinants. Okay, so having found our determinants, we need to now find Jacobian inverse of the function. So we simply find Jacobian inverse of x naught, y naught. This is going to be equal to, so you have, remember you take now the inverse of the determinants, just as we explained earlier. You have 1 all over the determinant, which is negative 3.436 minus 3, minus 3.436, please, minus 3.436. Now multiply by the transpose of the major diagonal of the matrix. So I will simply take 2 and replace 1, take 1 and replace 2. So instead of having 2 on the major diagonal, I will simply have 1 here. And instead of having 1 here, I will simply have 2 here. Then you negate the minor diagonals. So this is 2.718. It becomes minus 2.718. Again, this is 2, so it becomes minus 2. And then you have this. So if you multiply these two together, this simply gives us the Jacobian inverse of that given matrix, right? So this is going to be equal to, let us find 1 divides negative 3.436, just to break everything down, right? So 1 divides negative 3.436. So that gives us approximately 0.2910. You have negative 0.291. Now this multiplies by 1, negative 2, negative 2.718, and 2. Okay, so the Jacobian inverse of x naught y naught is now going to be equal to, so we simply now expand this bracket, negative 0.291 multiplied by 1, that gives us okay, we simply have negative 0.291. Negative 0.291 multiplies negative 2, so negative cancels negative, so we simply have 0.582. So we have here positive 0.582. Again, negative 0.291 multiplies negative 2.718. Negative cancels negative. So we simply find 0.291 multiplies 2.718. That gives us approximately 0.791. So we have approximately 0.791. And finally, negative 0.291 multiplied by 2. Again, that gives us this time around, it gives us negative 0.582. So this gives us the Jacobian inverse of that matrix. Now, having found the Jacobian inverse of the matrix, we know what our x naught and y naught is. We can now couple into this equation and obtain the first root of that given equation. Is this simple? So let's try it and see. Okay, so it means, remember, we are considering when n is 0. So this becomes x0 plus 1. That gives us x1. That's our first iteration. So the formula we now have, x1 y1 is going to be equal to, remember, you have here xn and n is 0, so that gives us x naught y naught, and x naught is simply 1, y naught is also 1. You have this minus, you have Jacobian inverse of that matrix, Jacobian inverse of that function at the initial guess multiplied by the value matrix of the function at the initial guess. And this is our Jacobian inverse obtained here. So this multiplied by the matrix of the function, and we obtain the matrix of the function to be this over here. So we simply couple them together. So this minus Jacobian inverse, we have the matrix here, negative 0.291, 0.582. So we have negative 0.291, 0.582. Then down here we have 0.791, 0.791, negative 0.582. This multiplies by the matrix of the function negative 2 and 2.718. So we have negative 2 and we have 2.718. You simply have this. Okay, so this means, okay, I think I can take this off. Let me create space here. So this simply means that x1 y1 is now equal to, remember, we have 1 1, this is minus, so we simply what, this is now a 2 by 2 matrix multiplying a 2 by 1 matrix. So remember, the whole of the row multiplies this entire column plus the whole of this row multiplies this entire column. So this is going to be, remember, the whole of this row multiply this entire column, and then you have the whole of this row multiplying this entire column. If you do that, you're going to have, so this gives us negative 0.291 multiplied by, the first element here is negative 2 multiplied by negative 2 plus, again, you have 0.582 multiplied by 2.781. So you have 0.582 multiplied by 2.78, 718, please. 2.718. Okay, that settles the first row. Same thing, the whole of this row multiplied by this column. So I have 0.791 multiplying by -2. So 0.791 multiplies -2 plus, again I have -0.582 multiplies 2.718. So -0.582 times 2.718, and you have this. So the matrix becomes this. So my first iteration for x and y is equal to, remember, 1 1 minus, so let's evaluate this matrix now and see what we are going to obtain. So in the first case, negative 0.291 times 2, negative cancels negative, so I'll have a positive value there. So that product simply gives us 0.582 plus, we find 0.582 multiplies 2.718. That gives us 1.582 approximately. So I have 1.582. Okay. Next, I evaluate the second row. So I have 0.791 multiplied by -2. 0.791 multiplied by -2. This simply gives us 1.582. So negative 1.582. Okay. Then I have negative 0.582 multiplies 2.718. 0.5 multiplies 2.718. That gives us 1.582. So we have negative 1.582. 582. Okay. So x1, y1 is equal to, I have 1 1 minus, so let's evaluate this matrix now. This gives me 0.582 plus 1.582. So I have 0.582 plus 1.582. That simply gives me 2.164. I have 2.164. Over here, I have negative 1.582 minus 1.582. Negative 1.582 minus 1.582. That gives me negative 3.164. So I have negative 3.164. Okay. So you already know when two matrices are subtracting, especially one 2 by 1 matrix are subtracting, it means the first element in the first row subtract the first element in the first row for the other matrix, and the second element in the second row subtract the second element in the second row for the other matrix. So this simply will give us, this is equal to, I have 1 minus 2.164. So 1 minus 2.164. Then I have 1 minus 3.164. Minus becomes plus. So this gives me 1 plus 3.164. Okay. So this simply implies that the first iterative values for x1 and y1 is going to be equal to, so let's see now, 1 minus 2.164 gives us negative 1.164. Again, 1 plus 3.164 gives us 4.164. So this simply implies that x1 equals minus 1.164 and y1 equals 4.164. So with this now, we've gotten the first iterative value for x and y. We repeat the whole procedure again using now x1 and y1 to obtain x2 and y2. So let's carry out the second iteration and see. All right. So now we carry on with the second iteration. And for this case, n is now going to be equal to 1 and not 0. So the first thing is to find the matrix of the function now at x1, y1. Okay, find the matrix of the function at x1, y1. Okay, so first of all, we need to find the function, because the matrix of the function now becomes it becomes f of x1, y1, and g of x1, y1. So we need to find the values of the function at x1 and y1, right? So we can do that here. So we find f of x1, y1. This is equal to, so we'll have x squared plus y squared. And x1 here gives us negative 1.164. So we have negative 1.164 squared plus 4.164 squared, that is for y squared, minus 4. So let's see what f of x1, y1 gives to us. Let's punch everything together. So everything gives us approximately 14.694. Okay, next we find g of x1, y1. So this is going to be equal to we have exponential x, which is exponential negative 1.164 plus y, which is 4.164 minus 1. So let's see what g of x1, y1 gives to us. I'll punch everything all together. So everything here gives us 3.476 approximately. So we have the matrix of the function is simply equal to, for the first function, 14.694, 14.694, and for the second function we have 3.476. 3.476. So this gives us the matrix of the second function. Okay, having found the matrix of the second function, the next is to compute the Jacobian of the functions at point 1, that's x1 and y1 now. Let's compute the Jacobian of the function. So the equation still remains the same for Jacobian. It doesn't change. So this is supposed to be 2x and this is 2y. And for the second case, we have exponential x, then we have 1. So this remains constant. So we simply now find the values at each of the points of x and y obtained now. So we are using now x1 and y1 to compute the Jacobian. So you have 2 times x1, and remember x1 is 1.164. So we simply have 2 times negative 1.164. That gives us negative 2.328. 328. So okay, so that's for 2x. Then for 2y, remember y1 is 4.164, so you have 2 times 4.164. That gives us 8.328. We have 8.328. Okay, next is exponential x, and x is negative 1.164. So we simply have exponential negative 1.164. That simply gives us 0.312. You have 0.312. Then here still remains 1, right? So here remains 1, and you have this. So this is now the Jacobian of the function. The next thing to do is to compute the determinant of the Jacobian. So remember, the measure diagonals multiply minus the minor diagonals. So measure diagonal here is negative 2.328 multiplied by 1. So I have negative 2.328 times 1 minus the minor diagonal. So I have 0.312 multiplies 8.328. So 0.312 multiplies 8.328. So let's evaluate everything and obtain an answer. Negative 2.328. Of course, multiplied by 1 still remains negative 2.328 minus 0.312 multiplies 8.328. So upon evaluation, everything gives me negative 4.926. I have negative 4.926. 6. So this gives us the determinant of that matrix. Next is to now obtain the Jacobian inverse. Okay, and to do that, we simply take the inverse of the determinants. So you have 1 all over negative 4.926, negative 4.926. Multiply now by the matrix of the Jacobian, the transpose of the major diagonal, and the negation of the minor diagonals. So I will transpose the major diagonals now. Negative 3. So sorry guys, my mic went off there. So I'll just quickly run through this so you can catch up to what we are. So we have to transpose, okay, transpose the Jacobian matrix by exchanging the minor diagonals, right? So the 1 was initially here and negative 2.328 was actually here. So you transpose the two of them, send negative 2.328 here, then send 1 over here. Then you negate the minor diagonals and you have this. So when you take the ratio of the inverse of the determinant, you're simply going to have 0.203. Use this value now to multiply all the elements in the matrix. So 0.203 multiplies, sorry, negative 0.203 multiplied by 1. That gives us negative 0.203. Negative 0.203 multiplied by negative 8.328. That gives you this value, and as well every other element you have in the bracket. So this simply gives us what in the matrix, sorry. So this simply gives us the Jacobian inverse, just like we did in the first case. Okay, this gives us the Jacobian inverse. So if you have the Jacobian inverse now, you have the matrix of the function, you simply plug into the formula to find the next iteration. Remember, the second iteration is when n is equal to 1. So that means xn plus 1 becomes x1 plus 1, that is x2. Same thing as y becomes y2. So you have it here, x2 y2 equals, remember, xn here becomes x1, yn here becomes y1. Okay, and we have the values of x1 and y1 here, negative 1.164 for x1 and 4.164 for y1. So you have these two values here. Again, it says minus the Jacobian inverse matrix multiplied by the matrix of the function. The Jacobian inverse matrix gave us this. So you simply see it here. That's the matrix multiplying by the matrix of the function, which actually gave us this. And you simply see that here. So all we need to do at this point, x2, y2 equals s1, y1, which is this, minus, we simply what activate the multiplication of 2 by 2 matrix versus 2 by 1 matrix, right? If you do that, you simply have this entire row multiplied by this entire column. So this element multiplied by this element plus this element multiplied by this element. And that's what we have here. So this entire row multiplied by this entire column. Same thing, this entire row multiplied by this entire column. So you have this element multiplying by this element and then plus this element multiplying by this element, and you have this. And upon evaluation, you simply have, okay, we've evaluated the top and we have this. So we're about to evaluate the second row. Okay, so second row is 0.063 multiplies 14.64 694 plus 0.473 multiplies by 3.476. So let's do this and see. So everything gives us approximately 2.570. So we have 2.570 approximately. Okay, so this simply now means that x2, y2 is now equal to, so you know, when two matrices are subtracting themselves, especially a 2 by 1 matrix, when they are subtracting themselves, it simply means each of the elements are subtracting themselves. So I have negative 1.164 minus 2.895. So you have negative 1.164 minus 2.895. Same, I have 4.164 minus 2.570. So 4.164 minus 2.570. So let's do this and see. So we simply have x2, y2 to now be equal to, so let's evaluate the first row, negative 1.164 minus 2.895.
That gives us negative 4.059.
So we have negative 4.059.
Next, we evaluate 4.164 minus 2.570. That gives us 1.594.
We have 1.594. So this simply implies that x2 is equal to negative 4.059 and y2 is equal to 1.594.
Okay. Alright guys, so the values for the second iteration simply gives us that x2 and y2. So this is what will happen. Just to save time, I'm going to give you the value. I'm just going to display the entire iteration and the point where it converged. It converged after about 7 iterations. I've solved it completely. So I'm just going to display the entire iterations and the answer. So you can go and continue trying it and to ensure if you're going to have the same result that will be displaying right on the screen. Okay. I'll just simply display the result now. So you can go on and use the same approach. All you need to do now is repeat the same procedure again. Find the matrix of the function at this new point now, x2 and y2. Find the Jacobian of the function also at x2 and y2. Repeat them to obtain your third iteration. That's x3 and y3 till it converges. So I will share the answer now on the screen. So you go ahead and try it out to see if you're going to have the answers just as I have it on my screen. All right, guys, so that's it on Newton-Raphson's method involving nonlinear equations. In the next video, I'm going to be showing you a simple approach to this because most people might not really be able to compute the Jacobian inverse procedure. So I will show you a simple approach to this. We're going to be solving this same question, but using a different approach, which is quite easier and simpler than this. I'm sure you want to be a part of that video, so do well to tap the subscribe button right now and turn on your bell notification so you don't miss out on that video when it drops. In the meantime, if you're new to the channel, do well to subscribe, like this video, comment nicely, and share to your friends. I will see you in the next video. Cheers.